So you've probably heard the term graph database thrown around a lot, right? Usually it's covered in all this technical hype. But what if I told you the core idea is, well, pretty simple? That's what we're going to do here. We're going to build a really clear mental model so you can walk away knowing what they are, why they even exist, and what kinds of problems they're actually built for. And to get there, we're going to lean on one single question. Seriously, this one question is going to guide us through this whole thing. And it is this: is the problem you're trying to solve mainly about records, or is it mainly about relationships? Keep that in your head. Okay, so let's start where most of us start. When you hear the word database, what pops into your head? For a lot of us, it's tables, right? You know, nice, neat rows and columns, and we learned all the clever ways to connect them, things like foreign keys and joins. That's kind of the default worldview for data. And hey, let's be super clear. That model, it's incredibly powerful for a reason. When you're dealing with structured stuff, isolated records like user accounts or invoices, the whole relational model works beautifully. It's clean, it's efficient, it's totally reliable.
But things start to get a little awkward when our questions change. What happens when the most important answers aren't tucked away inside one single row? What if the real gold is in the messy web of connections between all those rows?
Let's make this really concrete. Say you want to find a single user in a table. Easy, right? You just look up their row. Simple. Now, what if you want to find that user's friends? Okay, a little more work. You do a join between two tables. It's manageable. But what about finding the friends of their friends of their friends? Whoa, now all of a sudden you're chaining together these massive, complex joins. Every single hop in that relationship adds another layer of complexity. I mean, it still works, but it starts to feel really clunky, and it can get super expensive for the computer to figure out.
And this right here, this brings us to the absolute core idea. A graph database isn't some new kind of hardware. It's not a different kind of hard drive. The deep difference is all about how the information is organized. It's about what the system treats as a first-class structure, as something that's truly important.
So, how does this graph model actually work? You know what? Let's just build one. Right now, it all starts with something called a node. A node is just a thing, an entity. It could be a person, a scientific claim, an experiment. Think of it as the noun in our data story. But honestly, the nodes themselves aren't where the magic is. The magic is in how we connect them. And for that, we use an edge. Now, an edge isn't just a line on a whiteboard. It's a meaningful relationship. It has direction. This claim supports that one. This experiment contradicts another. The edge is the verb that makes the data come alive.
And then there's one more piece. We can add context using properties. These are just little bits of data, attributes, that can live on a node or, and this is really important, they can live on the edge itself. So a claim node might have a property like a confidence score of 0.9. Or a site's edge could have a property telling you the source. These are the adjectives and adverbs. So you have nodes, edges, and properties, nouns, verbs, and all the juicy context. That's it. That's the whole model.
And this really shows the big philosophical shift, doesn't it? A graph database is built on this fundamental idea that reality, well, it's not just a big bucket of things. The real meaning, the actual story, is found in the structured relationships between all those things.
Okay, so let's apply this to something real, like scientific discovery. I mean, think about the kinds of questions scientists ask. They're almost always about connections, aren't they? Like, which evidence supports this claim? Or what path links this experiment all the way to this conclusion? Or maybe which results actually contradict this belief? See? These are all fundamentally graph-shaped questions.
This gets us to a really powerful idea called path thinking. With a graph, you can literally trace the entire history of an idea. It might start with a source document, which leads to someone's interpretation, which generates a new claim. Then an experiment comes along and updates our belief about that claim. This whole chain, this path, is something the database sees as a single thing you can ask questions about.
Now check this out, because this is where it gets really cool. Think about contradiction. In a lot of systems, if two things contradict, that's an error, right? Something you have to fix or overwrite. But in science, a contradiction is hugely important information. And in a graph, it's not an error. It's just a meaningful relationship, a specific kind of edge connecting two nodes that tells a really crucial part of the story.
So what this means is that a belief in a scientific claim, it isn't just a number floating in space. It sits inside this incredibly rich network. It's being propped up by all the supporting evidence, and it's being pulled on by all the contradictory findings. A graph lets you see and analyze that entire evidence neighborhood all at once.
Okay, so let's circle back to that core contrast we started with. The relational mindset, the world of tables, is always asking a question like this. What rows match this condition? It's a filtering process, right? You're trying to narrow things down from a big list.
The graph mindset, on the other hand, asks a totally different kind of question. It starts with a single thing, a node, and asks, what's connected to this? What does its neighborhood look like? What paths lead into it, and what paths lead out? It's a process of exploring outwards.
So, you can see the crucial thing here is choosing the right structure for the job. If your problem is really dominated by structured individual records, users, billing, stuff like that, then a relational database is absolutely the natural fit. But if the core value of your system comes from all that connected meaning, like tracing scientific claims and their evidence, well then a graph starts to feel like a much more natural way to see the world.
And this is so important to remember. A graph database isn't some magic bullet that replaces everything else. It's not inherently smarter. It's a very specific and very powerful structural answer to a certain kind of problem. Problems that are absolutely packed with relationships. It's all about picking the right tool for the job. And that really brings us to the big takeaway. The reason graph databases matter, the reason we're even talking about them, is for those times when the real job of your system isn't just storing things, but understanding how all those things are connected.
So I'll leave you with this question, something you can take back to your own work. When you look at your own data, the stuff you work with every day, what do you really see? Do you see a collection of records, or do you see a web of connected meaning? Because your answer to that, it tells you everything about which kind of world your data really lives in.